Today we're going to talk about implicit differentiation, and this is a technique that we often use when our expressions are not written explicitly as functions. So far in our studies, we've been working with functions that were defined explicitly, and by that I mean we have y equals, and then the function is written over here on the other side in terms of x. So y equals 2x squared minus 7x plus 6, or y equals sine of 2x. Essentially, when we say explicit functions, I'm going to write that up here, explicit. When functions are defined explicitly, there's a y equals, and then there's x stuff over here. For functions that are defined implicitly, the x and y stuff is all mixed up. And an example of that is the equation for a circle, which written explicitly or implicitly is not really a function, it's a relationship. But we know that we can have an expression, x squared plus y squared equals, we'll say 25, right, r squared. That makes a circle of radius 5. It's not a function, but at any point on this curve, we do have rates of change. And oftentimes, it's nice to be able to get a formula for the rate of change at a particular point. In other words, we like to be able to take the derivative of this thing. And that's what implicit differentiation is going to allow us to do. So I'm going to start by actually working on implicit differentiation for x squared plus y squared equals 25, and then we'll do a few other examples so you can see how this technique works. So we're starting here with this relation x squared plus y squared equals 25, and we want to come up with a formula for the rate of change, which is the derivative. And so our technique goes something like this. What we're going to do is we're just going to start doing derivatives by whatever rule we happen to need. In this case, we're just going to need power rules. So when I look at 2x, the derivative there, when I look at x squared, the derivative there is 2x. So I just start by doing the derivative. So I did the derivative of x squared and I got 2x. Then there's a plus sign. And y is a different kind of a thing. Y is a function of x. So when I do the derivative, I'm going to have to follow the chain rule. And by that I mean I'm going to do the 2y, right? Because you bring the 2 down, you write down the y, and you subtract 1. But because y is a function of x, the chain rule says I have to multiply by whatever the function y, the derivative of whatever the function y is. Now, I have no explicit description of what y is. So all I can do to indicate that I'm going to put the derivative there is actually put dy over dx. You could also put y prime, but that's going to get a little confusing because we also have the letter y in our expression. So to differentiate between the letter y, the variable y, and the derivative dy over dx, I'm not going to use y prime, I'm going to use dy over dx. So using the chain rule, because I'm taking the derivative with respect to x, the derivative of y squared is 2y times dy dx. And I'm going to keep moving along this relation. There's an equation, equal sign next. And now I have to do the derivative of 25. The derivative of 25, since that's a constant, is 0. And a lot of times people forget to write a 0 there. But whenever there's a constant, you write it down as derivative equals 0. So I did the derivative of 25. I'm just indicating with my little red arrows that in each case I am writing the derivative there. Okay, so now we have this expression. Remember, our goal was to get a formula for the rate of change. So what we're going to want to do is solve for dy dx. We want to isolate dy dx. So I'm just going to, from here on out, just do some algebra. So to start, I'm going to subtract 2x from both sides to eliminate this term. And now I have 2y dy dx equals negative 2x, because 0 minus 2x is negative 2x. Then, remember, I'm still trying to isolate, oops, that's supposed to be a highlighter, trying to isolate dy over dx, so I'm going to divide both sides by 2y. And when I do that, I end up solving for dy over dx, which is our derivative, our rate of change formula. Now, over here, negative 2x divided by 2y, that's just negative x over y. And this is my formula for the derivative, for the rate of change at any point on that relation. And it's okay if my derivative formula here has x's and y's in it, right? Our original formula had x's and y's mixed up in it up here. So it's okay for the derivative formula to have x's and y's in it. And what this formula is saying is, at any point on this circle of radius 5, if you want to know the slope at the point, in other words, if you want to know the slope of the tangent line, you just plug in the negative x coordinate divided by the y coordinate, wherever you happen to be located. For example, I happen to know that this point down here is 0, comma, negative 5, because it's a circle of radius 5. And I happen to know that that tangent line is horizontal there, so it should be a slope of 0. So the way we would do that is we'd plug in negative 0 over negative 5, compute that, and get 0, which is true. So this line has a slope of 0. So my formula works. This technique of implicit differentiation just says, start doing derivatives like you normally would, but any letter that's not x, that's not your independent variable, when you take the derivative, you have to follow the chain rule because those other variables are functions of x. In this case, what I'm talking about is this y was a function of x, so when I did the derivative, I had to multiply by dy over dx. X is an independent variable. You can think of it, we could actually do this anywhere, right? For x, it would be dx over dx. Oops, that's not a... And in thinking of these in terms of little numerators and denominators, dx over dx, that's just 1 anyway, so it goes away. So you could force yourself to think in those terms, and anytime you took a derivative, you'd put the d of whatever letter it is over dx, and the dx's would all cancel, but the dy over dx doesn't cancel, and that's the one you want to solve for. That was way too many words for that problem, but that's the idea. Let me show you a couple other quick examples. So here's an expression, xy equals 42, which includes a product. And I put this in here on purpose because you're going to end up running into this product a lot. It'll probably be part of a larger function, but I'm focusing on this one here because we can also do this problem explicitly, and I want to show you that you get the same answer. So I'll do the implicit differentiation over here to outline the technique. And when I do that, we're going to actually ask you to remember the derivative of xy because it comes up a lot. So when you write down xy like this, it turns out this is a product. It's x times y, right? And so when we do products, we assign u to be one of the variables and v to be the other variable. I don't want to write that there. So v is the y, so I'm going to put v equals y. And then to get organized, we do the derivative of u prime. That's just 1. But the derivative of v, because y is a function of x, the derivative of v is 1 times dy over dx, which is dy over dx. Okay? And now when we write out the product rule, we're going to have v times u prime, so that's y times 1, plus u times v prime, which is x dy over dx. And I'm letting you know that that thing right there is going to come up a lot in the problems that we do because the product xy is in our expressions quite often, so it's a good idea to remember that one. Now, we're not done with this problem, though, because we have an equals 42 here on the other side, and the derivative of 42 is 0. So in terms of solving for dy over dx, we're not done yet. Just like the last problem, we're going to isolate dy over dx, so I'm going to do minus y from both sides. And I'll end up with x dy over dx equals negative y. And then when I solve by dividing by x, I get dy over dx equals negative y over x. Similar to, but not the same as the function we just worked with. Now I want to show you how we could write this thing implicitly and get a very similar answer. So let me show you what I mean. This function, if I solve for y, can be written as 42 over x, or better yet, 42x to the negative 1. And if we were doing the derivative y prime, we would do the power rule and get negative 42x to the negative 2, which is a better way of writing that is, that was bad English. A better way of writing that is negative 42 over x squared. So my derivative is negative 42 over x squared. And you're probably thinking, hey man, we got negative y over x on this side down here. That is not the same as negative 42 over x squared. And I say, oh yes it is. So watch this. Since y equals 42 over x, if I'm looking at negative y over x, that's just going to be negative 42 over x over x. And remember, this is a complex fraction, and that does equal negative 42 over x squared. So this negative y over x is the same as our derivative that we found explicitly, which is negative 42 over x squared. We're going to get the same answer for the slope at each point, whether we do negative y over x or if we do negative 42 over x squared. You're going to get the same slope value. Okay, let me show you one other example. I wanted to show this xy piece. Let me show you a problem where it includes that xy piece. So here's a really nasty one. It's got all kinds of our greatest hits. You'll notice that product that I mentioned, xy, is included here. We've got a composition because we've got the sign of xy. We've got a power rule there, and everything's mixed up. So this is definitely a great candidate for implicit differentiation. But this one's not easy, so just keep in mind this is a bit of a stinker. Okay, so as we start doing derivatives, we're going to do the derivative of y squared, which is 2y, but because y is a function of x, we have to multiply by dy over dx. Then we do the equal sign. We do the derivative of x squared, which is 2x. And then dx over dx cancels, so I'm not going to write that. And then we have this composition, the sign of the product xy. So we've done the chain rule enough now to see where this thing is headed. It's going to be the cosine of xy times whatever the derivative of xy is. That's how the chain rule works. So I'm just going to write that down. It's cosine of xy, because cosine is the derivative of sine, times the derivative of xy, which we just computed in an earlier slide. That was y plus x dy over dx. And we do that by doing the product rule implicitly. So just keep in mind, this piece is because of the chain rule, and I stole the expression from another slide because we already did the derivative of xy once. There's no reason for us to do it again. We did the product rule with u's and v's, and this is what it worked out to be. Okay, now, how in the world do we solve this thing for dy over dx? The bad news is we have a dy over dx over here, and we have a dy over dx over here. So we've got to get those terms together so we can solve. So there's going to be a lot of nasty algebra coming. Good news, I love to do nasty algebra, so I'm going to see what I can get away with here. All right, this is all one big term. I'm going to distribute the cosine of xy to each of those so I can break that up. So I'm not going to mess with anything over here yet. 2y dy over dx, remember I'm trying to solve for dy over dx, equals 2x. And when I distribute cosine xy, the first term I get is y cosine xy. And then there's a plus sign. And then the second term I get is x cosine xy dy over dx. And in order to solve for dy over dx, when I have 1 on the left of the equal sign and 1 on the right, I need to get those together. So I'm going to subtract this entire term over to the other side. And when I do that, I get 2y dy over dx minus x cosine of xy dy over dx equals this stuff here, which is just 2x plus y cosine of xy. Okay, now how in the world do we solve this thing? Well, we're just being patient here and noticing that there is a common term, common factor in each of these terms. So I'm going to factor that out. And I'll have my dy over dx times the 2y here minus the x cosine xy here equals the 2x plus y cosine xy. And I wish I'd have been a little more careful how big I wrote, because I'm at the bottom of this slide and I am one step away from finishing this thing. So I'm going to take this line right here, this last line, I'll rewrite it on the next slide, and then I'll finish the problem. So as I said, I'm going to rewrite that last line, which you can see here, and then to finish this off, all I need to do is divide this out. So I'm going to divide both sides by 2y minus x cosine of xy. And if I do that on both sides, I'm done. I have isolated my derivative, dy over dx, and I've found that the formula for that dy over dx is 2x plus y cosine xy. I'm going to fix that just a little bit here. Cosine xy. I don't think I fixed it after all, but that's supposed to say cosine xy. Divided by 2y minus x cosine of xy. And this is now our derivative formula. This is the formula that will give us the slope at any point on that original crazy relation. As long as you know the x and the y coordinates, you can plug them into this formula and you can get a value for the slope. That's what implicit differentiation has done for us here. So this is an example of a pretty nasty problem. There's a lot of algebra going on, but there's nothing that's beyond what we've been working on. You just have to be careful. And this one had a composition and it had a product, and we handled it okay. It'll take practice, but you'll get there. So I want to just take the last slide to just summarize our strategy for doing implicit differentiation. So as you can see, I stole this out of your textbook, but these are the steps that we want to run through each time we have to do implicit differentiation. So first of all, the main step, the first step is we're just going to start doing derivatives. This word differentiate means do the derivative. It's the act of doing derivatives. So we're going to differentiate both sides of the equation with respect to x. That means anything that's not x, we have to treat it as a function and use the chain rule. That's what this part says. Anything that's not x, specifically y, is a function of x that you have to differentiate using the chain rule. After you've done that, we're going to collect the dy over dx terms to the left. I usually do it to the left, but in other words, we're going to solve for dy over dx. And then we'll write that final expression after we do our algebra to get it on one side. Okay, so that's implicit differentiation. We're going to practice a whole bunch of these, and in particular, in a couple of lessons, we're going to take this implicit differentiation that we've learned and use it along with our physics to solve what's called related rates problems. So that's something to look forward to. Just don't ask anybody who's ever taken calculus about related rates. They might scare you. Okay, that's enough from me for now. Good luck with the problems. Let me know if you have any questions. Take care.